Good afternoon. We were discussing the heat exchanger in last two classes. Well, we will continue the discussion. What we were discussing about the parallel and counter flow heat exchanger, simple shell and tube type. Let us start with that. Again, let us have a shell and tube type like this, simple shell and tube, double pipe. This is the tube side fluid, and tube side fluid in and tube side fluid out. This is the shell side fluid in and out, shell side fluid, shell side fluid, shell side fluid. Let us also draw side by side the parallel counter flow arrangement. This is this one the parallel flow, the both shell side fluid and the tube side fluid flows in the same direction, but this is the I am not writing again the tube and this thing again. This is a counter flow type, shell end. Now, the temperature diagram along the length of the tube, if you see length or area, whatever way you think it, area, it is better because ultimately you will deal with the area for heat exchange, L or A. Here what happens, the hot side fluid, if we consider hot side tube or shell, doesn't matter, the hot fluid, not hot side, hot fluid has a decrease in temperature and the cold fluid increases the temperature in the same direction. Let us consider this is the hot and cold. Let this temperature, H is the subscript for hot I told, and 1 is the inlet here, parallel flow TH2 is the hot outlet. Similarly, cold inlet is TC1 and cold inlet is TC2. Then in this diagram we can show TH1, TH2, TC1, TC2. This is the picture. The assumption is that the fluid temperature is uniform across a section and heat is being, this is the hot fluid, sorry, this arrow I should show here, it will be difficult there, I will draw something else. This is the cold fluid, this is the hot fluid diagram temperature, this is the cold one, and at any section the heat is flowing like this from hot to cold. This is the temperature. Here the situation is this, the hot fluid flows like this from TH1 to TH2 in a direction. Let the similar way the hot fluid flows through the tube and the cold fluid flows in the opposite direction, for which this is known as counter flow, hot and cold. Here also the heat transfer takes place from hot to cold because of this temperature difference. Now this type of problem, this type of arrangement, one type of problem is like this. First of all, let us see that the energy balance or heat balance is like this. If I consider m dot H as the mass flow rate of the hot fluid and m dot C is the mass flow rate of the cold fluid, in both the cases m dot H and m dot C, with this nomenclature the total heat that is transferred between the hot and cold, m dot H, and if C stands for the specific heat at constant pressure, is TH1 minus TH2, that is the heat which is being given by the hot fluid equals to m dot c cc Tc2 minus Tc1. Now this is the first line of energy balance. Now the one type of problem is this, that the conditions are like this. The property that Ch and Cc are usually known, thermodynamic properties, specific heat. Now the operating parameters or conditions are that flow rate of the hot fluid, its inlet temperature, its outlet temperature, flow rate of the cold fluid, its inlet temperature and outlet temperature. Now out of these 6 quantities, you see we have one equation only relating to these 6 quantities. That means 5 are independent and 1 is dependent. Usually the mass flow rates of both hot and cold are given in some class of problems along with 3 temperatures. Means implicitly I know the 4th temperature. That means all these 6 quantities are given. This type of problem means that the rating of the exchanger, that means the operating conditions as far as the heating and cooling load, that means how much heat has to be transferred from the hot fluid to be cooled or how much heat has to be gained by the cold fluid to be hot, is known because the mass flow rate and the temperatures are all known. 3 temperatures are known, along with the mass flow rate I can find out the 4th one. So that this is known as, in this terminology, in the field of heat exchanger, the heat exchanger is rated for its heating and cooling load. What is to be found out for this type of problem? We are interested to find out what surface area is required. If we consider a simple double pipe heat exchanger, either parallel or counter, what is the surface area required? This is known as sizing problem. Means the heat transfer from the heat load side is rated. That means the total load is given. How much heat has to be transferred is given. We want to know the size. Size means the surface area required for that heat transfer. This we can find out definitely if we write this equation, Q is equal to UA delta Tm. Just I discussed last class that we know overall heat transfer coefficient. The concept of overall heat transfer coefficient was told earlier, which is the sum of the heat transfer coefficient of fluid sides, both the sides fluids plus the conduction resistance. And if we see the resistance, that sum of the resistances are the equivalent resistance, if we assume that overall heat transfer coefficient is constant along the flow, then we can write the rate of heat transfer in this fashion: UA delta T, some mean temperature difference, where A is the area based on which overall heat transfer coefficient is defined. That means basically this is the definition of overall heat transfer coefficient, but it is other way in practice. The overall heat transfer coefficient is given, so that practical problem we have to find out the area based on which EU is given when we know the Q. But the only difficulty here compared to simple convection problem, as we have done in the class, that this temperature difference, sometimes we have seen the flat plate, free stream, all are constant temperature along the flow. But here this delta T responsible for heat transfer changes from one section to other section. Here it is inlet and outlet because both are flowing in the same direction. Here from one section. That means there should be some mean delta T, mean of these two extreme difference of delta T. This is one delta T, this is another terminal. The mean of terminal delta T is in such a way that could define this equation. So to find out that delta Tm, we have to do a small mathematical exercise. Let us consider the parallel flow case and a elemental area in this exchanger dA, where we have a change in hot fluid temperature, which is denoted by dTH, and also this is a decrease in the temperature, and at the same time there is an increase in the cold fluid temperature through that dA area here in the exchanger, through which the change is dTc, and here there is a amount of heat transfer delta Q, which is represented here. We can represent here also delta Q. That means a small elemental area delta dA, delta Q heat is transferred from the hot to cold, by which the hot fluid suffers a differential decrease in temperature dTH, and the cold fluid suffers a differential increase in temperature dTc. Then we can write that del Q is equal to m dot HCH into minus dTH, because TH is decreased, is equal to m dot CCC dTc. This decrease and increase of temperature with reference to the direction of one particular prescribed direction, and here the prescribed direction in a parallel flow is the direction of flow, because both the fluids are flowing in the same direction. Then we can consider that change in hot fluid temperature is a decrease and it is an increase. And it is interesting to see that if you integrate this equation, you get this one, because if you integrate this minus dTH in the direction of the flow, it will be TH2 minus TH1 is dTH. So minus of that will give this, and dTc will be TC2 minus TC1. That means simply a differential form of this equation we are writing here. Okay, now we make a very simple algebraic, at a primary school level algebraic manipulation, that dTH minus dTc equals to what? dTH minus dTc is del Q. dTH is minus, dTc is also minus, that means minus del Q 1 by m dot HCH plus 1 by m dot CCC. dTH minus dTc, clear? This can be written as d of TH minus TC is algebraic step minus del Q 1 by m dot HCH plus 1 by m dot CCC with the nomenclature I have told. Now from the definition of heat transfer by this equation, the overall heat transfer coefficient, we can write del Q at that section is UdA into TH minus TC, because TH and TC are the hot fluid and cold fluid temperature at that section, infinite small section of infinite small area dA. So this has to be valid. So therefore I can substitute del Q here, and I can write d of TH minus TC, very simple, divided by TH minus TC is equal to minus U dA, dA I will write here, m dot HCH plus 1 by m dot CCC into dA. Clear? Okay. You may or may not take the note. This is given in any textbook. Just it will also be good that if you just go on seeing, can find out any inadvertent mistake if by chance I make. It's not always necessary to take the note, but you can take also the note because it is given in any book. You see the philosophy. So this is all right. Now if you integrate both these sides with respect to dA, so left side represents the temperature difference. This is the way it is expressed between this inlet and outlet with respect to this parallel flow heat exchanger. Then the left hand side become ln TH minus TC, it will be TH2 minus TC2 divided by TH1 minus TC1. Okay? Any problem you can ask me. Okay? And this side will be minus U 1 by m dot HCH plus 1 by m dot CCC times area. Okay? So this is clearly this thing. Now I will substitute 1 by m dot HCH and 1 by m dot CCC from here. There are two equations. If you consider Q into picture, Q is this and Q is this. That means this equality gives 2, and ultimately I can substitute 1 by m dot HCH plus 1 by m. What is 1 by m dot HCH? It is Q TH1 minus TH2 by Q, and m dot 1 by m dot CCC is TC2 minus TC1 by Q. And if you do it, it's very simple, then you get this, ultimately this equation, and Q will come. Q is equal to UA TH2 minus TC2 minus TH1 minus TC1. I am not unnecessarily wasting time by doing this. Just simple, if you do that, you will get this one, TH2 minus TC2 divided by TH1 minus TC1. Automatically you will get this. If you just substitute 1 by m dot HCH plus 1 by m dot CC in terms of Q from here. That means here the entire thing is a mean temperature difference, delta T. Now if I define delta T2 as the temperature difference at the outlet here in case of parallel flow, that is equals to TH2 minus TC2, and delta T1 is TH1 minus TC1, then this can be written as Q is equal to UA delta T2 minus delta T1, and it will be always positive whether delta 2 and delta T1 vary with their respective magnitudes, higher and lower, because plus minus will be adjusted. If delta 2 is more than delta T1, both numerator denominator will be positive, and if it is other way, both are negative. Okay, so therefore we can write this equation like this, and this quantity is known as LMTD, that is log mean temperature difference, because the log is coming log mean temperature difference. The log mean temperature difference, LMTD, which is defined as delta T2 minus delta T1 divided by, that means this fashion, the difference of the two delta T's at two terminals divided by the ln of their ratios. This is LMTD. So Q is equal to, therefore you see that if the exchanger is rated fully by its heating and cooling load, prescribing this thing so that I know Q, then I can find out its surface area if I can determine LMTD. So if I know the definition of LMTD, which satisfies this equation, that means it is that average delta T between the two terminals which satisfies this equation. And if I am provided with the value of the overall heat transfer coefficient, I can determine the size of the exchanger. This is known as typical sizing problem. Clear? Clear to everybody? Now there is a clue. If, very important, it is a counterflow heat exchanger, how you will derive it. Now first of all, counterflow heat exchanger is also the same formula, but what is delta T2? For a counterflow heat exchanger, the generic formula is this one. Delta T2 in counterflow heat exchanger is any side you can take in counter flow heat exchanger. There is no inlet outlet reference because it is hot fluid inlet, it is cold fluid inlet. Let us make this delta to TH2 minus TC1. Then delta T2 will be TH2 minus TC1. And what will be delta T1? Delta T1 will be TH1 minus TC2. Clear? How to derive it? I leave it to you as an exercise, very simple. How to derive this one? That means I have to come to this step where this will be UA into TH2 minus TC1 minus TH1 minus TC2 divided by ln TH2 minus TC1 divided by TH1 minus TC2, so that a generic formula will come out. LMTD is delta T2 minus delta T1, difference of delta T's divided by ln ratios of delta T's. How to do it? Very simple. I tell you the catch because I will not waste time. Here in this equation, if you take here one prescribed direction here positive, then dTH will be minus because it is decreased in this direction. Take the flow direction of hot fluid. Then dTc will be also minus. Because why? Because this is increasing in the negative direction. So therefore, both the things will be minus. It will be minus dTH, it will be minus dTc. So therefore, dTH minus dTc will be changed, which will be del Q 1 by m dot c dot minus 1 by m dot h ch. Change will be there. So accordingly, you can find out that there will be changes. Just only changes here. Very simple. That means this equation will be minus dTH and minus dTc. And think that if you integrate this, you will get the same result. This is clear because this is a energy balance, all are scalar quantities. Counter flow, if you integrate this minus dTH, dTH will be, this is a preferred, that is a positive direction. dTH will be TH2 minus TH1. So minus dTH is TH1 minus TH2. Similarly, dTc will be TC1 minus TC2. So minus dTc will be TC2 minus TC1. Therefore, integration of this with minus dTH and minus dTc for counter flow will give you the same result. So finally, when you will substitute this 1 by m dot CCC minus 1 by m dot HCH, because this will come, then you take the same equation. Only catch is that you have to express dTH minus dTc, because d of TH minus Tc, hot minus cold. Clear? So this is an assignment, everything I have told, that in a counter flow also you can do the same thing. But now the most interesting part of this equation, very interesting and very important too. I think you are intelligent, you can understand. Now the situation may come, two things you must remember, that a counter flow, parallel flow heat exchanger, if a heat exchanger is very infinitely long, this may be equal to this. Cold fluid outlet temperature can at best become equal to the hot fluid outlet temperature, I have told earlier, but not the hot fluid inlet temperature. But here, the cold fluid outlet temperature may be more than the hot fluid outlet temperature, even in a finite length, because here you see this temperature, there is no restriction that this will be lower than that, because heat is transferred this way. That means at this end of the heat exchanger, the temperature differential causing the heat transfer is from the inlet temperature of the hot fluid to the outlet temperature of the cold fluid. So as because they are flowing in the opposite direction, the cold fluid outlet temperature may be more than the hot fluid outlet temperature, which is not the case for the parallel flow. Another thing is there, if the product of M and C, M dot and C for hot and cold fluid becomes same. That means if m dot HCH is m dot CCC, their will be a situation for counterflow. The two curves will be parallel to each other, and ultimately delta T2 is equal to delta T1 is equal to delta T. So what is LMTD? What is LMTD? What is LMTD? Gone. What is LMTD? Anybody? Who told delta T? How? 0 by 0 form. So you can use the L'Hospital's theorem, taking the limit. In many ways you can prove it, that it will be delta T1 or delta T2 or delta T. Very simple to prove these things. That is also left to you. We can take delta T2 by delta T1 as x. You can write delta T1 into x minus 1 divided by ln x. Limit as x tends to 1, you will see this becomes delta T. Okay. So therefore, we can do it in various ways. X minus 1 by ln x, L'Hospital's theorem is a mental problem. X minus 1 becomes 1 and ln 1 by x, and in that case here it will be delta T1. This thing will be delta T1 into x minus 1, where x is delta T2 by delta T1, and we can write the denominator as ln x. Now limit of this as x tends to 1, sorry, not limit of this as x tends to 1, we have to make a L'Hospital's theorem differentiation. Again it is 0 by 0 form, until the 0 by 0 form gone. So we have to go for number of steps with that. So delta T1 divided by ln x is what? 1 by x. And limit x tends to 1. That means there are various ways to prove it. Sometimes you can prove that delta T2 minus delta T2 is delta T1 plus epsilon, and put it and take epsilon tends to 0. Denominator ln 1 plus x you can expand in a series ln 1 plus x type of thing, that is delta T1 by epsilon, and you can prove that limit will be delta T1 only. So therefore it is very important, these are school level tasks, that when delta T2 and delta T1 are same, under these circumstances mass flow rate capacity product is equal, then we have to have LMTD as this. And one information I give you in this respect, just an information, this can be proved analytically, but I am not going to prove, just as an information for an engineer. If delta T2 by delta T1 vary by a factor, ratio, which one is greater, depending upon that the ratio is within 2.2, then we can use the arithmetic average as the LMTD with 95% accuracy. Usually arithmetic average is higher than the LMTD. We should not use it, otherwise it will be over predicted. This will be over predicted. So therefore, LMTD and arithmetic average will be within 5% error, provided delta T2 and delta T1 varies. Varies means the ratio is within 2.2, and when exactly this is 1, ratio is 1, they coincide with each other. That means arithmetic average is equal to the LMTD, because arithmetic average is delta T1 or delta T2.